So thanks everybody for coming. This talk may be better termed, I call it UAV Traffic Management, or UTM, which is the acronym that is used primarily around NASA Ames, for example, is doing a lot of work in designing the next air traffic management system which incorporates UTM. But I think more generally we'd like to talk about autonomy in the airspace and kind of the issues and the challenges, both technologically as well as thinking about policy when you start to introduce autonomy into the airspace. And so I've got a little bit of an introduction here. This is actually an old slide. It's actually from Alex Bayan's PhD thesis, so that tells you, he's a full professor here now, so this was a while ago. But this is a snapshot from about 15 years ago of aircraft across the United States. Here we are looking at the Bay Area, and you can faintly see these sectors of airspace with aircraft moving in and out. And you see kind of the flows of traffic coming into the Bay Area airports. And you see also, aircraft sort of leaving and suddenly appearing, and it's in a loop, so they'll all disappear right now and start again, because that's just the period of time of the movie. But what we see here are aircraft in between the kind of what we call the higher altitude airspace. So above about 18,000 feet and below about 35,000 feet. So aircraft kind of in what we would call the en route airspace. Through individual sectors, each of these sectors is controlled by a human air traffic controller sitting on the ground, getting the information about where the aircraft are, what their flight plans are, so where they plan to be, and basically routing them, and we'll say manually. I mean, the controller is talking to the pilots over radio channels, approving their flight plan through the sector, adjusting if there's going to be some conflict between aircraft, and that's really the main role of the air traffic controller, to guide the aircraft as they go through and to maintain a conflict-free airspace. So that means that for all the aircraft in the airspace, all pairs of aircraft have to stay separated. And you can think about separation as basically being encoded by virtual hockey pucks around aircraft. So they have to stay, in the airspace that we're looking at, they have to stay 5 nautical miles laterally apart from each other and 1,000 feet vertically away from each other. And a violation of that is a severe condition. Okay, so what did I want to say about this? So actually, let me say something about one of the sectors. So the sector here is Sector 33. I've spent a lot of time in the air traffic control unit, in the unit that's controlling Sector 33. So there's an air traffic controller, there's a backup air traffic controller. In the next bay, there are air traffic controllers for the neighboring sectors, and it neighbors onto the Salt Lake sector. So that's actually over near Salt Lake City. This is located, well, it was located in Oakland, now it's near Sacramento. But basically the controllers here, they have a challenging problem, and you kind of see it in other places. What you see in the white lines here are routes. So these are jetways, they're well-defined jetways between these waypoints. And the air traffic controllers typically route aircraft along these jetways. So you kind of see that, although you do see a lot of off-jetway flight. And so one of the issues with Sector 33 is that there's quite a few points of intersection. So they see a lot of conflicts. That makes sense, right? Because you have aircraft coming from all over the country coming into land in the Bay Area airports. And so the air traffic controllers are typically monitoring these points and really thinking about how a good controller tries to touch each aircraft a minimum number of times, meaning tell the pilot fewest things as possible to get the aircraft to flow through the system and to not disrupt it too much. So the procedures, voice over radio, we talked about separation standards, human controllers, very much a human in the loop system. There is automation. The automation is largely on board the aircraft. So the pilots are, they're in control of the aircraft, but a lot of that control is being done automatically by autopilots. There is some automation in air traffic control, but it certainly doesn't match what you see on aircraft. So there are advisory systems for air traffic controllers that will look at the system and will propagate it and do conflict probes. Where are you likely to see a conflict? But it's typically, that part is run by the human. It's very much a human-in-the-loop control system. Okay. Why is it not an automated system, and what are the challenges to fully automate this system? And if we think about this, you know, if you, so we've had the ability to fly the aircraft in the system autonomously since about 1970, right? It's not, I mean, that's where autonomy first came in with, you know, jets and autopilots. But there are, and though autonomy is used a lot, pilots are sitting there and there's a lot of, you know, autopilot functionality, flight management systems, you know, there's really good autonomous functionality, there's still a human in the loop. And they actually have procedures where pilots have to fly an aircraft manually a certain number of times per month, for example, over time period, and the aircraft has to fly autonomously a certain number of times per month. That's just to keep everything certified. So the essential issue here in automating everything is that we can't anticipate everything that could happen. We don't have the ability to anticipate all possibilities of what could happen. I mean, when we talk about autonomous cars, this is the big issue, right? Unstructured environments. Here, I mean, it looks crowded because we're looking at, you know, the aircraft are really big if we look at the scale here. But it's relatively free airspace. These aircraft are flying through the air. And, you know, that makes a relatively safe system. There's time to correct if there's a problem. But still, we still can't anticipate everything that could happen, and so there's always been, and according to me, there, at least for the foreseeable future, there will be a human in the loop, both in the air when you have a, you know, a passenger jet, as well as on the ground. Good. Okay. So then, if we just move on again, these are sort of some background slides. So the main role of the controller is to keep the aircraft separated. And if you actually watch what controllers do, they tend to group aircraft together by conflict. So, you know, these two aircraft, if they're flying along a jetway at the same velocity, they're basically like one aircraft. So, you know, the procedures are that they will take a bunch of aircraft and they'll line them up, and then you can treat that whole group like one aircraft. These are the most critical because they're coming into one of these waypoints. And so the controller's attention is typically looking at those and figuring out which one to maneuver, how to resolve that, and then these aren't far behind. So they tend to group aircraft together when you think about cognitive models of controllers working with this system. And if you actually try, and this is one of the projects we had a while ago, if you try to build a model of an aircraft under human air traffic control, it's well modeled by this hybrid system, where you have basically a finite state machine of different control modes, and then in each mode represents the continuous flow of, you know, the dynamics of the system. So typically aircraft are flying at the speed that's optimal for their altitude, and the controller may slow them down or speed them up by a little bit to resolve conflicts. But they can't do that too much, or, you know, they're flying at speeds which are not optimal for the altitude. So they might put them into detours or shortcuts, for example. A shortcut is a mode that you know, we introduced because we saw it used a lot. Kind of the worst possible thing to do is a holding pattern, and I'm sure you've been in holding patterns. Those are typically not used in en route airspace. They're used as you're coming into busy airports, and they have actually specific points. Like out in Point Reyes, there's a holding pattern that, you know, I've spent a lot of time on the holding pattern, for example. Vector for spacing, that's like, you know, if you really have to slow down, they'll deviate you in a triangular pattern from your route. Altitude change is also a bit of a last resort, unless you have to do an altitude change anyway, like you're coming into land, because you typically want to keep aircraft at the altitude that you know, that their weight is. The density of air corresponds to, you know, flying at an optimal density of air corresponds to a particular weight of the aircraft. So you have these altitudes that you're typically flying at. All right, so what do we take away from this? Small set of control actions. You know, it's kind of a well-defined system. That's not too much for a particular, I mean, there's continuous dynamics, and there's one of these for every aircraft, and then you have the composition of them for maybe all 15 aircraft in a sector of airspace that a controller's looking at. But it's a small set of control actions they would like to do as a control policy in frequent deviations from nominal, and they group together by potential conflict. Okay, so why is this becoming a very, it's always been an interesting research area, looking at automating air traffic control. It's becoming much more fast-moving now than it ever has been before. And that's really for two reasons. One is that there's a lot of pressure being put on the FAA in the US, on the FAA and on the research branch behind the FAA, which is a large part of what NASA does, to think about how we might modernize the air traffic control system to allow for autonomous vehicles. And so, for example, Amazon and Google have been very interested in how you might, what are the rules and regulations, and how might they influence those to be able to get UAVs flying through the airspace easily. And so, you know, just it's a little bit of a clean slate when it comes to introducing, or it comes to updating the air traffic management system for UAVs. And it's probably, you know, what we see happening now in terms of the sequence of sets of regulations that the FAA is putting out for UAV operation is that there's going to be a kind of separation of airspace. That, you know, there'll be UAVs, these are typically flying at low altitudes, not in commercial traffic, but of course where that's going to intersect are the large urban areas where you have airports, where you have aircraft taking off and landing, where you want to have, for example, a lot of deliveries, or you may want to. So just that, that delineation of airspace isn't always possible. And how do we design procedures for, in particular, thinking about introducing UAVs into the national airspace system? So when we're doing that, how much of the current structure should we adopt if we're thinking about, you know, say, a brand new UTM, or unmanned air system traffic management? So safety, we don't want the aircraft to hit each other, but, you know, typically there's nobody in those aircraft, right? They're small UAVs. We don't want them falling on people, so we typically don't want lots of them flying over heavily populated areas. So safety is an interesting thing to take a look at. The simplicity of the design, again, for the foreseeable future, there's going to be a human in the loop, even if it's just in a supervisory capacity, where the set of, you know, UTM controllers will be sitting on the ground monitoring what's going on in the UAV airspace. So how do you maintain a system that's both autonomous but is understandable by the people in the loop? And here, I mean, there's a real opportunity to integrate autonomy, and thinking about how we take, you know, real-time data, how we perceive that data, and how that affects the algorithms that are, you know, basically flying these aircraft. So they need to be able to adapt to new information. There's going to be a data-driven component. How do we blend data-driven with safety? Okay, so just some examples. This is an old project that we did in my group where we computed conflict zones in real time using reachability computations, and then we ran them on board each of, these are 4 quadrotors. This is kind of the earlier, I mean, these look historical when you see what's available now, but these are quadrotors that we built back in the late 90s, I guess, early 2000s. And we're flying them. We've got 4 students, 4 quadrotors. Each student is joysticking a quadrotor around, trying to crash into the other aircraft. The aircraft are running this collision avoidance protocol on board, where they're computing the reachable set with respect to all 3 of the other aircraft. And when an aircraft gets on board, or when it gets onto the edge of a reachable set of one of the other aircraft, then the autopilot takes over and guides the aircraft away. It won't let an aircraft into that conflict or the potential conflict zone. And then when the aircraft are safely separated again, the control is given back to the pilot. In a not very smooth transition. That wasn't actually the point of this project. It was more a demonstration of multi-aircraft collision avoidance using reachability. Okay, so another example, just bringing up some research examples of things that our group has done in this context. This is an idea we actually took. We were inspired by work that was done in the mid-90s here at Berkeley on the California Path Project on automating the inner lane of California's highways using platoons of closely spaced, fast-moving cars. And that would be an automated lane. So if you drove into that inner lane, your car and the control of your car would be taken over by a roadside controller that's basically putting you into a platoon of several vehicles that are driving close together. So we thought about that concept because when we looked at routing for UAVs, we looked at just this is sort of a separate problem, but we looked at the problem, say, of having a starting point, say, at a warehouse in Concord, and then delivery points in some of the Bay Area cities, and we imposed a cost map on the airspace that if you're flying over water, things are relatively cheap. If you're flying over wooded areas, which are sparsely populated, again, that cost it's a cheaper cost. It's expensive to fly over heavily populated areas, and it's really expensive to fly in airspace. So San Francisco, Oakland Airport airspace. And so then you run a shortest path algorithm with those cost maps, and what emerges, not surprisingly, are these trunk routes, like highways in the sky with short deviations into the expensive areas. So you kind of go all the way around here rather than across the kind of expensive area. And so the idea of highways led us to think about platooning vehicles, having UAVs that are typically adhering to these highways. So this is an idea. These routes can be calculated in real time. They can be recalculated in real time. And so the idea is to think about not having aircraft fly willy-nilly over spaces, but sort of organize them, but have an organization which is easy to update. But this, we presented this, and we got a lot of, excitement from NASA, but we also got some pushback from the environmentalists, thinking about, well, if you're flying over waterways, you're disrupting, bird life, water life, things like that. So, these are the kinds of considerations and policy considerations when we're thinking about a fresh design, or what I called before a kind of clean slate design of UTM. As we move forward with this, we introduced a control structure. So this is the platooning structure, where each, again, this is like what I showed before for the aircraft in the airspace. But here, this would be a control system for a UAV under this kind of automated or semi-automated platooning control, where there's a leader. You're either the leader of a platoon or the follower as a vehicle. If you join a highway, so if you merge onto one of those trunk routes, you have to be part of a platoon. You could be your own platoon, a single vehicle. A follower is basically a vehicle that's controlling itself with respect to the velocity of the vehicle in front. The nice idea here, and it's a nice one also from complexity, is if you have such an organization, then in terms of possible collisions, you only have to worry about the vehicle in front or the vehicle behind. So it much reduces the complexity of looking at n-vehicle collision avoidance becomes a pairwise collision avoidance problem, which is much easier to solve, and we can do that in real time in terms of that collision avoidance protocol that I talked about. If you're not on a highway, you can be a free vehicle, so you have to be able to join a highway. We can use altitude for faults. So a vehicle can go to a different altitude if it's faulty or if it's unable to follow the control protocol. So we spent some time studying this and generating the control laws, namely the transitions in this. It's a hybrid model. It looks like a finite state machine, but again, there's the continuous dynamics of the system evolving in each of those discrete states. And so we studied how to automatically generate the control transitions. We studied the safety and the robustness of this system. And just to show you some examples, this is a merge and join. All right, so it's we've got two vehicles here that are merging onto this highway, a red vehicle and a blue vehicle. And in each of those, I've plotted some sets of interest. Again, these are reachability computations that we did This is a target set for the red vehicle. Once it's in there, there's an automatic control law which will snap it onto a moving position on the highway. And this is its avoid set. It's looking at the relative, from its information that it's getting about the other vehicle, it's computing a relative safety. It has to stay outside of this set given the current relative dynamics. And so this would be the corresponding set for the blue vehicle. So it's trying to get into this set, but avoid this set here. And if you look at this protocol, so again, this is just emerging from that control law. Everything's autonomous here. You get this kind of organic motion in which you see these, this merging of a group of 5 vehicles onto a highway. The sets are all computed here, that they're following the same rules that I showed before. I'm just not plotting those sets so you can see this kind of merging onto a highway. So that's nice, but what can you do with that? You'd like to be able to demonstrate and analyze the robustness of such a protocol. So suppose you have vehicles that are not following these control laws. They're just going to, kind of force their way through an existing platoon on a highway. Basically, the protocol says that as soon as it touches an avoid set of another vehicle, it should avoid that. So it departs, the vehicles depart from the highway, and the vehicle, the intruder just goes right through the platoon, but doesn't come into contact or doesn't come into that, safety distance with any of the other vehicles. So this is something that we've done analysis on. We've presented it at NASA. They've been quite interested. And we also, we have a lab here, so we've been doing some of these experiments on our local, these are our crazy flies. And so you can, these are not just, it's a protocol that's implementable with current communication links that we have between the vehicles. So this is forming a platoon. Maybe the more interesting one is the intruder. Let's just run that one. So you see you actually see it quite starkly. The vehicles, there's an autonomous avoidance just based on the computed reachable set of the vehicles. And that's done in real time because it's really just looking at pairwise collision avoidance for this multi-vehicle problem. Okay, so those are a couple of the examples of things. We don't need to show this one. We've done. David mentioned that he's working on fast planning. We're now taking that reachability computation and we're integrating it in real time into online planning algorithms for vehicles. So the idea is that typical motion planners in robotics use very simple point mass models. Typically vehicle dynamics are more complex and we'd like to be able to account for that in planning, but we don't want to slow down the planners. So we pre-compute errors. We pre-compute buffers, which are really computed by the difference between point mass models and the kinds of dynamic models that you'd actually like to use in safe planning. And so we use that buffer computation. So once we've computed that, we can propagate that along the path. And we can do real-time planning like we were doing with point mass models, but we're maintaining this error computed using a reachable set calculation. And so that's done in real time. I'll just show one of the, so the computation is typically tough, but it can be done ahead of time. So we don't need to, we can do that offline, and then we can use that computation. So those are the examples of the computation for different tracking bounds. But we can use that computation in real time in planners. And one of the projects that David and others in the group who are working on this are doing right now are asking, well, if you're in free open space, it makes sense to use very simple models. You don't have a lot of constraints, you can do things fast. It doesn't matter if you're not very accurate. But as you get to narrow corridors, or you get to regions where other things are moving around, things that you might be uncertain about, you want to use a better model. You want to typically maneuver using, and there, the way you maneuver becomes more important. So you want to be able to use more detailed models. That's going to slow you down. So why not use fast planning in kind of open space and then slow that down according to these reachability calculations when you get to constrained space. And that trade-off can be done, we can compute when to do that trade-off and then how to prove that that's safe. And that's some of the things he's doing now. And it's neat how that complies. This is the connection with Tom Griffiths, who's also on this project, who's in cognitive psychology. how that links with, you know, what people do, fast and slow planning. You do things quickly if you don't care too much about it because you know it's fine, but when it starts to get, you start to have a lot of constraints, you slow down, you have to think about it. So it's kind of a neat analogy there. Okay, so finally in the last 2 minutes, adaptation to data. So as I said, when you're looking at UTM, it's not only safety now, you're going to have a lot more, potentially a lot more autonomous functionality. And that is going to be driven by data that you're receiving in real time. So you need to put perception loops in, and a number of you are working on integrating perception and control. But you'd also like to be able to maintain safety properties. So one of the research directions here is how to do learning based on perceived data, but maintain the kinds of safety guarantees that we've already computed. And so that's been another emphasis of research in our group. And essentially we're combining two things. We've got a safety calculation. We typically do that on a nominal model, usually a conservative model. And then we operate within the safety bound of that conservative model, but we use online learning to update the model. Now all sorts of really interesting questions come up, and this is where it links to kind of just, you know, policy. What's the right thing to do? So once we've updated the model and it's become maybe less conservative, how much do we trust that model so that we can do a recomputation of the safety to make it less conservative? And those are questions that, they're not just technological questions, right? Those are really, they're questions that are rooted in social science and have great implications on policy. So we've been working on, you know, this is just one experiment, this is kind of the end of the talk, but this shows a very much an in-lab experiment that we set up to illustrate the concept of safe learning. And what you might do if you're, you know, you have a nominal model. In this case, we only have one vehicle. It's not a collision avoidance scenario with other vehicles, but it's in what we call an envelope protection example. We've computed an envelope in the airspace that we'd like this vehicle to be in so that it's not in danger of hitting the floor or the ceiling. And it's actually doing it rather slowly, but it's gonna follow a step trajectory. As it gets near the ceiling, it's going to slow down. As it gets near the floor, it's going to slow down, right? So it's kind of a simple envelope. But the interesting thing in this example is that it's computed that envelope based on its own nominal model. And that nominal model doesn't include a disturbance, which is a big fan. And that big fan is going to be turned on right now by Kenny in the lab. And that's producing kind of a big disturbance, a wind disturbance in one part of the room. And so we have these two experiments were run sequentially and we're plotting them in parallel. But as the vehicle that's updating its safety envelope gets close to that disturbance, it shrinks the envelope. It notices it, it gathers that data in real time and realizes that it is measuring a disturbance that is outside the bound that it computed its original envelope on. And so now it's going to try to explore, can it actually go down a bit more? But it's staying safe while it's doing it. Whereas this one computed a safety envelope and it's not updating the envelope, so you see it getting buffeted around. So this is one of the first experiments we did, now really thinking about how do we take these ideas and expand them into other kinds of things that you're discovering in real time, like, you know, people walking in front of a car, for example. All right, so let's end this with, we talked about UAVs, and I'd really like to end this by talking about this kind of new vistas of personal air mobility. This is an exciting area now. I'm sure you've all heard about what's going on in the news, but the idea of a flying car has resurfaced. It's always been around. Shankar's always been a supporter of flying cars. And the idea is that with autonomy, you can actually design very smart flying cars. And, you know, it's not very cluttered in the airspace. So this has been proposed as a solution to the megacity traffic problem, where one could actually take a vehicle, like an autonomous helicopter, from one airport to another, say from Berkeley to Palo Alto, to or you know, San Jose, to avoid traffic, and then you would have some kind of Uber between, so Uber car to your heliport, Uber Air over to the other airport, and then Uber car again. So Uber is one, I'm using that as an example because that's one of the proponents. They've been working on, and so this has fueled a lot of work in electric vehicles, rotorcraft, so there's been a lot of work on the vehicle side here, and here's just some examples. Google is supporting Kitty Hawk. They've largely been flying over water. This is Sebastian Thrun's new gig. I think he's running Kitty Hawk as one of the things he's doing. A number of other really interesting aircraft concepts, aircrafts whose you see the use of rotors, for example. Aeromobile is a Slovakian vehicle that exists now. It's flying. I mean, they're all flying. This has maybe gone the farthest, although much of the work now, I mean, like 99% of the work has been done on the vehicle design. And now, even to try to get these things flying, even for tests, the policy is not there, how to integrate these into the airspace. So I put this up as the last slide, or the second to last slide. I just want to say thanks to a lot of the students who've worked on these projects. But as a sense that we're not just interested, when we talk about autonomy in air, we're thinking about the current aircraft, we're thinking about UAVs, and we're also thinking about these new vistas with autonomous taxis that could take people from one point in a megacity to another. Okay, so with that I'd like to conclude and just say, this has been supported by a number of projects, but it's this latest NSF, the PIRE project that we've been speaking about earlier in the day, that has been one of the drivers for thinking about the development of technology alongside with policy in different international contexts. So what are the variants between, say, two different countries, and how are they tackling that technology policy interface? Good, thank you. Now we're dovetailing with a center kickoff, but I think we're going to stay here, but if there are any quick questions that I can answer, and I'm going to stick around, so you're welcome to come and chat with me. Good, thank you.